We have learned about equilibrium as a general concept, and now we're going to apply what we learned to a specific type of equilibrium, that is acid-base equilibrium. So we have been going through some definition for acids and bases already when we covered the chapter about reactions in aqueous solution. And we talked about three types of reaction: acid-base reactions, precipitation, and oxidation reduction. So we're going to recall some concept that you should remember from the chapter. So the first definition in terms of in historical terms, and it's also the simplest, is the Arrhenius definition. So an acid is a substance that releases H+ when dissolved in water, and a base is a substance that releases OH- when released in water. And this definition works to some extent until they realize, chemists realized, that there were some substances that, despite behaving as acids or bases, would not necessarily fit in this definition. So because of that, they needed to have a larger, more comprehensive definition. That is the definition of Bronsted and Lowry. So for example, if you look at the example showing here, ammonia doesn't really have an OH- in the formula. So and yet you can see that it behaves like a base, because when you dissolve it in water and you use litmus paper, the litmus paper would turn, the pink litmus paper would turn blue. So that tells you that ammonia is a base. So in this new definition, the definition of the acid does not change much. It's still a substance that can release H+, but the base is defined as the substance that would accept those H+. So the acid-base reaction is a reaction in which there is an exchange of H+ ions from an acid to a base. Also, if you notice, in the definition is being dropped the solvent, so it doesn't say in water. So this allows to apply this definition also to solvents that are non-aqueous, and this is not so much of interest in your tribal class, but in an organic class you would have to sometimes use more often than so, you would use solvents that are not aqueous at all. But as we are going to see, there are still substances that are not included in the definition. And so we need to upgrade to a third and even more large definition. Is called Lewis. In the Lewis definition of acids and bases, is not so much about hydrogen ions being transferred, but rather an unshared pair of electrons being used to make a new bond. So bases are electron pairs donors. So for example, ammonia, if you remember the Lewis structure of ammonia, there is a lone pair. So that's how it's defined as a base. And an H+ that doesn't have, it's deficient in electrons, doesn't have any actually, it's an electron acceptor. Let's see some example to illustrate the Lewis definition of acids and bases. So let's start with BF3. Now you might remember that this compound was mentioned when we did Lewis structure and the octet rule, and we mentioned that there were exceptions to the octet rule. In particular, this is a particular example of an exception that's when you have electron deficient atoms. So if you write the Lewis structure for BF3, you will see that the central atom of boron has only 6 electrons, 2 per each bond around it. Now that formula has been simplified, eliminating all the lone pairs around fluorine. There should be 3 pairs of dots around each fluorine, but for sake of simplicity they have omitted that. Also, the other thing that you might have noticed is that the shape is kind of arbitrarily drawn, because it looks like there is a 180 degrees between 2 of the fluorine, and between the other 2 is 90. Actually, we know that because boron has 3 electron regions around the central atom, the shape is trigonal planar. So because it is deficient of electrons, it can act as a Lewis acid, and that explains why it in fact behaves like an acid. in terms of, reactions in solution. And so if he encounters a base, according to Lewis, so a substance that has a lone pair, so that is rich in electrons, like for example ammonia, they can react together, form a new bond between nitrogen and boron, and form what is called an adduct. So there are a couple of peculiarities here. The acid-base reaction is forming just one compound that is called adduct, Lewis adduct. The compound has a new bond, this bond here, that is a covalent bond, but it's a little bit of a weird bond because we have learned that you have ionic bonds when the electrons are completely transferred, or covalent bonds when two atoms would share one electron each and put them in the middle and form a bond with it. But here both electrons are coming from ammonia. So this is a kind of a special type of covalent bond where both electrons are coming from the same atom. It's called dative or coordination bond. Dative comes from the word datum, that means given. That's why when I give you a problem and I give you the data, we call them data, right? Another thing that I want to point out is the way ammonia has been drawn. It looks like it has the same shape as BF3, but we know that because there are 4 regions, the 3 bonds with hydrogen and the lone pairs, the shape of ammonia would actually be a tetrahedron. Another example is not so much this, but the one that's coming after. This is an acid-base reaction in which you can identify the acid and the base just by using Arrhenius, not even Bronsted-Lowry. The acid as is H that are very conveniently written in front of the molecule, so you know this is an acid. This is an hydroxide, so it's the poster child of bases, right? And they react to form a salt and water. Now, the same reaction it could be obtained by reacting the oxide of sulfur and calcium. You would still get the same salt, but no water, right? So it's much so it kind of makes sense that because due to the similarity of the reactant, let's say, and the fact that you get the same product, you can kind of anticipate that this must also be an acid-base reaction, but it's hard to see SO2 as a base or an acid and CaO as an ace or a base because you don't see those typical components like the H plus and the OH minus. Now you might remember from one of the first unit that SO2 it's a molecule in which you have a bond between 2 nonmetals, sulfur and oxygen. So this type of oxides with non-metallic oxide are covalent in nature. While this is an oxide between a metal and oxygen, so it's a metallic oxide, the bond between metal and non-metal is ionic, so this is an ionic bond. Now at that time I probably told you also that non-metallic oxide are acidic in nature and metallic oxide are basic in nature, and in fact if you add water to SO2 you get this acid. That's a hydroxy acid, and if you take CaO and you add water you get the hydroxide. So how can we use the Lewis definition to explain this reaction? So again we can see that the oxide ion from CaO is rich in electrons, so that's the donor of electrons, so that's the Lewis base, and it can use those electrons to form a bond in which both electrons are coming from the same source with sulfur that is deficient of electrons and is therefore the acid, the Lewis acid in the situation. And once again you get the adduct that is an ion and is calcium as a counterbalancing ion. I'm pretty sure there was something else that I wanted to tell you here, and oh yeah, I wanted to point out that in this type of reaction, to show the movement of electrons, it's very common to use these curved arrows. So for those who have to take organic chemistry, this is going to be something that would become quite familiar. So just to summarize, Lewis acids and bases are is the larger and more comprehensive definition of acids and bases. A Lewis base is a molecule that has a lone pair, so it's rich of electrons, and it can use those electrons to form a covalent bond with the other species that's a Lewis acid that has an empty orbital, so is electron poor. Okay, so let's go back to our acids, and we have learned to make a distinction between strong acids and weak acid, and we need to refresh that concept. So strong acids are completely ionized in water. So if I put a certain amount of nitric acid, every single molecule will separate into H+, or if we want to be more formally correct, H3O+, and NO3 minus, and there would be by the end of the reaction there would be no HNO3 left. So we write only one arrow in the reaction because the reaction goes one way only, unidirectional. It's not an equilibrium at all. So that means that if I have 0.1 mole per liter of nitric acid in the solution, as soon as I put the nitric acid in the solution, there is going to be no nitric acid left as such, and I will have 1 mole of nitrate ion and 1 mole of H3O+ ion. So what about weak acid? Weak acids instead are only partially ionized in water. Actually, the amount that ionized is quite small. So if we put 0.1 mole per liter in solution, and we have an equilibrium, so that's the double arrow, and the vast majority of the HNO2 is still going to be present in solution, and I have just small amounts of NO2 minus and H3O+. Notice the difference in the formula from the acid before. HNO3 is a strong acid, HNO2 is a weak acid. So for a weak acid, we have an equilibrium once it is dissolved in solution. So if we want to be rigorous, we need to write the molecule of water in the dissociation reaction. The molecule of water is the Lewis acid because oxygen has lone pairs, so it's rich in electron, and it can donate those electrons to the H+ of the acid, forming a covalent bond, and thus producing H3O+. If we go and write the equilibrium constant for this equilibrium, we should notice that it's an heterogeneous equilibrium because 3 species are aqueous, HA, A-, and H3O+ are aqueous, but water is liquid. Therefore, water should not appear in the equilibrium constant, and the equilibrium constant becomes just this. For weak acids, typically the value of that constant is smaller than 1. If it's larger than 1, it's what you would consider a strong acid, and you wouldn't even basically write an equilibrium constant. What if we, let's say we are a little bit lazy and we don't write the equation in this way, we just omit the water? Well, although formally not as correct, it doesn't really change any calculation because the equilibrium constant would just end up the same. So you need to know if an acid is strong or weak, and you should have memorized the 6 strong acids when we cover chapter 3. There are 6 strong acids for which everyone agrees upon, and then there is the chloric that has in fact an equilibrium constant of pretty much equal to 1. So depending on the book, sometimes that's included or sometimes is not. Because it's slightly controversial, if I ask you a question about weak acid or strong acid identification, I would not use chloric. But pretty much everything else that is not in that in that equation is going to be a weak acid. And pretty much every organic acid, so every acid that has carbon in the formula, that is either organic or is carbonic acid, but they are all weak. So here you see some examples. Acetic and formic are organic acids. And then you have hydrofluoric, HF, and hypochlorous. So you might notice that all the acids, as simple acid formed by combination of hydrogen with an halogen are strong except HF. That still make it an extremely toxic and dangerous compound, but is not a strong acid, is a weak acid. You might remember it's the acid that was used in the popular TV series Breaking Bad for the whole issue with the corpse that was put in the bathtub with the HF. There is an interesting video on YouTube that you may want to have a look, and I put the link here. It's by a group of chemists from the University of Nottingham, and they make really interesting videos. And this one is about testing the credibility of that episode of Breaking Bad. Of course, they didn't use human bodies; they used chicken legs. But it can be kind of cool to go and watch that experiment and the explanation with it. Strong bases are much easier to remember because as hydroxide of group 1 and group 2. Now you may have a hard time with barium hydroxide and strontium hydroxide because although they are strong bases, they are poorly soluble. As I have multiple times pointed out, solubility, being soluble or not, and being a strong or a weak electrolyte and therefore a strong or a weak base are two separate concepts. You may have substances that are very soluble, like acetic acid, but they are weak acid. You may, so weak electrolyte. You may have substances that are very soluble, like sugar, but are non-electrolyte. You may have a substance like strontium hydroxide that is a strong base, therefore is a strong electrolyte, but is very poorly soluble. So you may not be able to make a solution of strontium hydroxide that has a very high molarity, but the amount that you dissolve is going to be completely dissociated. So if these are the strong bases, what are the weak bases? Well, any hydroxide that is not from group 1 and group 2 is going to be a weak base. Problem is they're pretty much insoluble, very poorly soluble. Most of the examples that you see are, well, there is ammonia. Ammonia is sort of the grandmother of all the bases, of all the organic bases. And then there are a bunch of organic compounds that contain nitrogen and are basic, but they're always weak. Here I just put some example. Basically consider ammonia, right? That would be the Lewis structure of ammonia. Now imagine you remember it's a tetrahedron and doesn't have square angles as in the Lewis structure. The Lewis structure doesn't tell you, I mean, it helps you calculate the shape, but the way they are normally written is in an exam is not indicative of the angles. So don't assume that because a formula is written like that and there is a question about what's the angle of the bonds, that's 90 because it's been drawn like that. You need to count the electron regions, and this 4, and therefore is a tetrahedron. So let's imagine we take away the hydrogen, right, from the ammonia. Now we have those 3 bonds. Those 3 bonds can connect nitrogen to 2 hydrogen and a chain of carbon, or 1 hydrogen and 2 chains of carbons, or even 3 chains of carbons. And those chains of carbons can be super simple, like here when the chain, you have only 1 chain connected to the nitrogen and is made of only 1 atom of carbon. But here you have 2 atoms of carbon, so you can make the chain longer, you can make the chain branched, the chain may have a cyclic structure. So easily you see that the number of molecule that you can create becomes extremely large. You may have also, so this is an example where two bonds are used to bond with carbon and only one stays bond with nitrogen. Here you have all three bonds of nitrogen engaged with carbon. Then you can have two nitrogen included in the same molecule. Now, all this large variety of compounds containing nitrogen with this type of structure, they're all basic. There are other organic compounds containing nitrogen that are not basic, but you don't have to worry about those. They also share in common a normally pretty unpleasant smell. The most common description of it is that the smell of rotten fish. In particular, the name that these two have, putrescine and cadaverine, kind of give you a hint that they are not properly fragrant. You may notice that those formulas are written in a kind of a funny way. When you start writing really big formulas, people get lazy and they don't want to write all the atoms. So what are corners represents an atom of carbon plus all the hydrogen that you can fit, basically. And so you can see that it gets really busy as opposed to just drawing those zigzag lines. So in acid-base reaction, we can identify conjugate acid-base pairs. Okay, so let's take this reaction with between nitrous acid and water. So you can see that there is a connection between HNO2 and NO2-. It's like a before and after, right? So the only difference between those two is the presence or the absence of a nitrogen. So what happens is that by losing a nitrogen, HNO2 becomes NO2. So that constitutes acid-base, conjugate acid-base pairs. So I represented the acid in red and the base in blue. There is another one that is the pairing of water with H3O+. Yet again, the only difference is one atom of hydrogen. So the H3O+ is the conjugated acid of the base H2O. And the reaction happens because you have a transfer of hydrogen from the acid to the base. The terms conjugated comes by yolk, the yogurt, cum yogurt from Latin. So it's if you have been in the countryside, it's a very obsolete agricultural tool, but you can still see it used by Amish farmers. It's used to connect two animals, like two horses or two ox, to the plowing machine, through the plower. And interesting is, although it's not a very cheerful image, is the word that is used in Italian to indicate the two people are married. Sounds more like a penitence rather than a pleasant thing. So let's identify some conjugated acid-base pairs. So you need to look for molecules that differs only for one hydrogen, right? So you see that in the first example on the top, water is a base because it's accepting the proton from the HNO2. In the example at the bottom, water, the very same molecule, is an acid because is donating the H+ to the base ammonia. So water can behave either as a base or an acid, depending on the circumstances, depending on the partner, let's say, that is encountering. If it's in the presence of a base, it will behave like an acid. If it's in the presence of an acid, it will behave like a base.